Welcome back to the deep dive. We're really thrilled to have you with us today because we are looking at a stack of sources that, well, on the surface, it might sound like a cure for insomnia.
Right, yeah, it sounds a bit dry at first glance.
It does, but it's actually hiding some of the most intense, high-stakes information we've ever covered. We're unpacking an exam bank today.
A massive one. 325 highly specific questions.
Yeah, exactly, from an advanced diploma in industrial safety, or ADIS. Now, before you roll your eyes at the idea of, test prep, stick around.
Seriously, stick with us on this one.
Because when you strip away the whole multiple choice format, what you're left with is the hidden rule book of human survival.
That's a great way to put it.
It's the literal science of keeping fragile human bodies alive in modern environments that are, frankly, designed to crush or burn or poison us. Okay, let's unpack this.
It's a phenomenal collection of material. If you look past all the regulatory jargon, what you're really studying here is masterclass in risk management and human psychology and systemic engineering. The rules in this exam bank were literally written in blood.
Which is pretty grim to think about.
It is, but it's true. Every single regulation or mathematical threshold we're going to talk about exists because at some point, someone just didn't understand the physics of the environment they were in.
Right.
This is a philosophical framework about how we protect ourselves from our own industrial creations. And the lessons apply just as much to how you organize your garage as they do to a massive chemical refinery.
I want to start with that core philosophy, actually, because the material forces you to completely rewire your vocabulary. Like, we all use the words hazard and risk interchangeably in daily life, right?
Oh, constantly.
You might say a slippery floor is a big risk. But in the industrial safety world, treating those two words as synonyms is a fundamental mistake.
It is the most critical distinction in the entire field. A hazard is simply the source of potential harm. It's just a constant state.
Okay, give us an example.
Let's use an industrial scenario. Imagine a multi-ton steel beam suspended 50 feet in the air by a crane.
Okay, so massive weight dangling up there.
Exactly. That suspended load is a hazard. It has immense potential energy. Risk, however, is the calculation of likelihood and severity of that harm actually reaching a person.
I see.
So if that crane is operating in a completely empty, barricaded exclusion zone, the hazard is massive, but the risk to human life is zero.
Because nobody's underneath it.
Right. The risk only increases when you make the decision to walk under the suspended beam.
So managing that risk is basically the entire point of the safety industry. And the source material details a really specific framework for doing this called the hierarchy of controls.
Yes, the hierarchy of controls.
I spent a lot of time looking at this because it completely upended my assumptions. I mean, if you ask anyone on the street what workplace safety looks like, they'll picture a hard hat, right? Or steel-coat boots and safety glasses.
The standard uniform.
Yeah, but this hierarchy ranks the methods of control by effectiveness. And that gear, personal protective equipment, or PPE, is dead last.
Dead last.
Why is the gear we associate most with safety considered the absolute weakest link?
Because by the time a piece of PPE is actually doing its job, every other protective system has already failed.
Wow.
Think about it. If a brick falls from a scaffold and hits your hard hat, the hazard has already reached you. You're just relying on a thin shell of plastic to absorb the kinetic energy and hoping it's enough.
Hoping your neck doesn't snap.
Exactly. The hierarchy demands that you start at the top. The absolute best control is elimination, completely removing the hazard.
So instead of lifting that steel beam over a pedestrian walkway, you just change the site plan so the crane operates somewhere else entirely.
Precisely. And if you can't eliminate it, you move down a step to substitution, like replacing a toxic solvent with a water-based cleaner.
But what if the job physically requires the dangerous tool or the heavy load? Like, you can't substitute it.
Then you move to engineering controls. You build a physical barrier. Or you install a ventilation system to suck the fumes away before they ever reach the worker.
Got it.
And if you can't engineer the danger away, you rely on administrative controls.
Which is changing human behavior, right?
Yes. Rotating shifts. So a worker is only exposed to a noisy environment for 2 hours instead of 8. And only after you've exhausted elimination, substitution, engineering, and administrative controls do you finally hand someone a pair of gloves or a hard hat. PPE is the ultimate last resort.
That reframing changes everything. It really means safety is a design problem, not an apparel problem.
Perfectly said.
And tracking how well those designs work brings us to the math of disaster. The material introduces this concept called Heinrich's accident triangle.
Hmm.
It's a ratio, right? 1 to 29 to 300.
That's the one.
This implies that for every one catastrophic major injury, there are 29 minor injuries and 300 near misses. A near miss is, well, it's when a wrench falls off a scaffold and smashes into the concrete 2 inches from someone's foot, rather than hitting their shoulder.
Right. And if we connect this to the bigger picture, the absolute gold mine for any safety professional is that base layer of 300 near misses.
Why the near misses specifically?
Because human psychology makes us want to ignore them. If the wrench misses you, you wipe the sweat off your forehead, say you got lucky, and just go back to work. You don't report it because no one got hurt.
Out of sight, out of mind.
Exactly. But safety engineers view those 300 near misses as free lessons. They're the warning signs. If you can build a culture where workers actually report the wrench falling, you can fix the toe board on the scaffold today.
Which prevents the one fatality that was statistically guaranteed to happen tomorrow. That ties directly into how companies measure success. The sources talk a lot about lagging versus leading indicators. I always hear corporate executives throw around terms like LTIFR, the lost time injury frequency rate.
A classic lagging indicator.
Right. But what does lost time actually mean in reality?
Lost time is a very specific, pretty grim metric. It means an employee was injured so severely that they couldn't report for their next scheduled shift.
Ouch.
Yeah. So a lagging indicator like LTIFR is essentially looking in the rearview mirror. It's measuring how many people you have already failed to protect.
Whereas leading indicators are proactive.
Right. They are the metrics you track to predict the future. Measuring the number of near-miss reports or the hours spent on safety training or the frequency of equipment audits, those are leading indicators.
So you want high leading indicators to force your lagging indicators down to zero.
That is the whole goal.
It's wild how much of this is about fighting things before they ever happen. Let's pivot slightly to a totally different kind of invisible threat. The sources dedicate a massive section to health, hygiene, and chemicals.
Oh, this section is fascinating.
When we imagine chemical exposure, I think the Hollywood image is someone spilling a bubbling vat of acid on their arm. But the data shows that the most common route for chemical exposure in an industrial setting is actually inhalation.
You just breathe it in.
Right.
And because the lungs are so incredibly efficient at transferring whatever you breathe directly into your bloodstream, the regulations around airborne hazards are deeply mathematical.
Yeah, you're dealing with an absolute alphabet soup of exposure limits.
You really are. The foundation of this is the TWA, or time-weighted average. This is calculated over a standard 8-hour workday. It dictates the average concentration of a chemical vapor that a worker can safely inhale day after day without adverse health effects.
But a factory isn't always a controlled average environment. What happens if, say, a valve gets stuck and there's a sudden massive release of a solvent?
That is exactly why the STEL exists, the short-term exposure limit. This is a much higher allowable concentration, but it's strictly measured over a 15-minute window. You might be allowed to breathe 10 parts per million of a chemical all day under the TWA, but your STEL might allow 50 parts per million, strictly capped at 15 minutes.
So it recognizes that our bodies can process brief, acute spikes of toxins.
Yes, but only if they're immediately removed from the environment afterward to recover.
And these time calculations apply to invisible physical forces, too. The exam questions on noise exposure are relentless.
They really drill down on the math there.
They do. The baseline permissible limit is generally around 85 to 90 decibels for an 8-hour shift. But the source points out that noise is logarithmic, not linear. Every single time the noise level increases by just 5 decibels, the permissible exposure time is sliced exactly in half.
And that math is terrifying when you apply it to a real work environment.
How so?
Well, if a machine runs at 90 decibels, you can work your 8-hour shift safely. But if a bearing starts to fail and the machine gets slightly louder, jumping to 95 decibels, your safe working window is instantly reduced to 4 hours.
Wow.
If another piece of equipment turns on and pushes the ambient noise to 100 decibels, you only have 2 hours before you start suffering permanent, irreversible nerve damage in your ears. The math accelerates incredibly fast.
Which makes the rules around emergency response even more vital. There was one rule in the chemical safety section that really stopped me in my tracks. I'll call it the 10-15 rule.
I know exactly the one you mean.
If a facility has hazardous chemicals, an emergency eye wash and shower station must be located within exactly a 10-second travel distance from the hazard. Now, imagine a scenario where a pressurized line bursts and a highly corrosive solvent splashes across a worker's chest. They have 10 seconds of pure panic to blindly navigate to the shower. But the second half of that rule is the brutal part. Once they pull that shower lever, they are required to stay under that flushing water for a full 15 minutes.
It's an agonizingly long time.
15 minutes standing fully clothed under cold, high-pressure water while your skin is potentially burning. It really drives home how aggressive these substances are. You aren't just rinsing soap off.
No, you're trying to fundamentally dilute a chemical reaction happening at the cellular level.
That's terrifying.
That level of chemical aggression is why the global labeling system leaves absolutely no room for misinterpretation. Industrial environments use the GHS, the globally harmonized system, which relies on 9 distinct pictograms.
Right, the symbols on the barrels.
Yes. A skull and crossbones is not just a generic warning. It strictly denotes acute toxicity. It means a single exposure could be fatal.
Whereas an exclamation mark is different.
Right. The exclamation mark is used for less immediate threats, like skin irritants or mild allergens.
And if you need to know exactly how to handle that chemical, you don't just guess based on the picture. You pull the SDS, the safety data sheet.
The holy grail of chemical safety.
I found it interesting that the material stresses how rigid this document is. An SDS always has 16 standardized sections, no matter who manufactures the chemical or what country it comes from.
Uniformity is key.
So if you're a safety officer and you need to know what respirator to hand your team, you don't read the whole manual. You flip straight to Section 8, which is universally dedicated to exposure controls and personal protection.
You also have to engineer a solution for when that chemical inevitably tries to escape its container. The rule for secondary containment is a great example of defensive engineering.
Oh, the berms and trays.
Yes. If you have a primary tank holding 1,000 gallons of a toxic liquid, the concrete berm or spill tray built around it cannot just hold 1,000 gallons. It must hold 110% of the largest container.
Why the extra 10%?
That extra 10% is crucial. If a tank fails catastrophically, the liquid doesn't just flow out, it surges. You have to account for the physical displacement of the fluid, the wave action of the spill, and even rainwater that might already be sitting in the berm.
Here's where it gets really interesting. We've talked about invisible chemicals and sound waves, but the exam material also dives deep into the raw, visible forces of nature. Let's talk about fire and electricity.
2 forces you never want to underestimate.
We all learned the fire triangle in grade school, right? You need fuel, oxygen, and heat. But industrial firefighting introduces the fire tetrahedron.
Right, it adds a 4th side to the triangle.
Exactly. There's a 4th hidden element keeping the fire alive, the uninhibited chemical chain reaction.
And understanding that 4th element is how modern extinguishing agents work. They don't just cool the fire or smother the oxygen, they interrupt the chemical reaction at the molecular level.
But before you deploy any extinguisher, you have to categorize the fuel. The material is very strict on this.
Extremely strict.
Class A fires are ordinary combustibles, wood, paper, cloth. Class B is flammable liquids and gases. Class C is electrical. Class D is combustible metals, like magnesium burning at thousands of degrees. And Class K, or F, depending on your region, is for commercial cooking oils.
It's not just trivia either. Mixing up those classes will get you killed.
Really?
Oh, absolutely. If you spray water on a Class A wood fire, you cool the heat and put it out. Simple. But if you panic and spray that same water onto a Class C electrical fire, the water acts as a conductor and the current travels straight up the stream into your body.
Oh, man.
And if you spray water on a Class B liquid fire, the water sinks beneath the burning oil, flashes into steam, and violently ejects the burning liquid across the room.
The most terrifying fire phenomenon detailed in the sources, however, has to be the BLEV. BLEVE, the boiling liquid expanding vapor explosion.
Yes. A nightmare scenario for a safety engineer.
It occurs when a sealed tank holding a pressurized liquid like propane is exposed to extreme external heat, usually from an entirely separate fire burning outside the tank.
Right. So the fire is basically cooking the tank from the outside.
That's exactly it.
The liquid inside begins to boil, creating massive internal pressure. Eventually, the structural integrity of the steel tank weakens from the flames and ruptures.
And then?
In a fraction of a second, the pressurized liquid depressurizes, flashing instantly into a massive cloud of vapor, which then ignites. It creates a shockwave and a fireball that can level an entire facility.
Unbelievable. Let's pivot from the explosive power of fire to the silent speed of electricity. The material gets deep into the physiological differences between alternating current, AC, and direct current, DC.
People usually assume high-voltage power lines are the only real threat.
Right. But the exam focuses heavily on why AC is inherently more lethal to the human body.
It comes down to how your nervous system operates. Your brain sends electrical impulses to command your muscles. AC power, alternating current, cycles back and forth, usually at 50 or 60 times a second.
Yep.
When an AC shock hits you, it intercepts your nervous system and causes sustained muscular contraction. Your muscles violently lock up.
So you're trapped.
Literally, this is why a victim cannot let go of an energized wire. Their brain is screaming to open their hand, but the AC current is overriding the signal, holding the hand clamped shut around the source of the shock.
The micro measurements associated with this are horrifying. The threshold for the let-go current, the absolute maximum amount of current where an average person can still voluntarily release their grip, is between 6 and 10 milliamps.
Just a tiny amount of electricity.
To put that in perspective, a standard little USB phone charger puts out over 1,000 milliamps. If the current crosses into the 50 to 200 milliamp range, it induces ventricular fibrillation.
That's when the heart loses its rhythm.
Yeah, the rhythmic beating of the heart is completely scrambled into a chaotic flutter, and blood flow stops instantly.
And this is why the path of the current is just as important as the amperage. The material notes that a hand-to-hand shock is exceptionally dangerous.
Because it goes across the chest.
Exactly. If you touch a live wire with your left hand and ground yourself with your right hand, the electricity doesn't just flow into you, it seeks the fastest path out. It travels up your left arm, directly across your chest cavity, straight through the heart, and out the right arm.
And it doesn't even require you to touch a wire to get electrocuted. The concepts of potential explained in the material are fascinating. Touch potential makes sense. It's the voltage difference between an energized object you touch and the ground you are standing on. But step potential is the voltage difference between your 2 feet.
Imagine a power line falls to the dirt or lightning strikes the ground nearby. The earth itself becomes highly energized at the point of impact, and that voltage ripples outward in concentric circles, getting weaker the further away it travels.
So if you're walking away from that downed power line and taking a normal wide step, your back foot is closer to the power source than your front foot. That means your back foot is in a zone of higher voltage than your front foot. The electricity will literally enter your back leg, travel up through your pelvis, and travel down your front leg just to bridge the voltage gap between the earth beneath your 2 shoes.
It uses your body as a bridge.
That is why emergency protocols tell you to keep your feet glued together and shuffle away. You're minimizing the step potential to 0, so the current has no reason to travel through you.
Moving from invisible forces to massive physical structures, the material dedicates a large section to the physical gauntlet of construction sites and machinery.
The rules here are incredibly strict regarding gravity and confined environments. Fall protection is a huge focus. You don't need to be working on a 50-story skyscraper to require a harness.
Not at all.
The rules mandate fall protection starting at just 1.8 to 2 meters. That is roughly 6 feet.
A very standard height.
And the geometry of a simple ladder is regulated. You must place it at a 1:4 ratio against the wall, which creates a perfect 75-degree angle for stability.
And you have to maintain 3-point contact at all times while climbing. 2 hands and 1 foot, or 2 feet and 1 hand. No carrying toolboxes up the rungs.
Furthermore, work at height isn't just up to the worker's comfort level. The rules explicitly state that elevated work halts completely when wind speeds reach 20 to 25 miles per hour.
Then you have the regulations for entering what's called a confined space.
Which isn't just a small room.
Right. A confined space is an area with limited entry and exit, not designed for continuous human occupancy. Think of the inside of an industrial boiler, a grain silo, or a sewer main.
Okay.
The environmental controls here are absolute. Before a human being steps foot inside, the oxygen levels must read exactly between 19.5% and 23.5%.
That's a very narrow window.
Extremely narrow. If it drops below 19.5, you risk asphyxiation. If it rises above 23.5, the air becomes oxygen-enriched, turning every piece of clothing or speck of dust into a massive fire risk.
And the order in which you test that air is highly rigid. You can't just toss a multi-gas meter in and read the screen. The atmospheric testing must be done in a non-negotiable sequence. First, you test for oxygen. Second, you test for flammable gases. Third, you test for toxic substances. Why does the order matter so much?
Because the equipment relies on physics to work. If you test for flammability first, but the space has 0 oxygen in it, your flammability meter might give you a false 0 reading because the sensor itself requires oxygen to combust the sample gas and measure it.
Oh, wow.
You'd think the space is safe, climb in and immediately suffocate. You always verify oxygen first so you know your other instruments will function correctly.
That level of methodical checking brings us to machinery. Let's say you need to climb inside a giant industrial press to perform maintenance. You use a procedure called LDO, lockout, tag out.
A vital procedure.
You turn off the power, and you put a physical padlock on the electrical breaker, so nobody can accidentally turn it back on while you're inside. But the exam questions emphasize that Kia Lotara is not just about cutting the electricity. It's about neutralizing all forms of stored energy.
What's fascinating here is how easily we forget about mechanical physics. Yes, you killed the power, but did you lower the 2-ton hydraulic press to the floor?
Because if it's still elevated, gravity is stored energy.
Precisely. Does the machine have massive internal springs that are tightly compressed? Does it have pneumatic air lines under pressure or electrical capacitors holding a lethal charge long after the power is cut?
So lockout, tag out requires a technician to physically bleed, block, or dissipate every single ounce of kinetic and potential energy before the machine is considered safe.
Yes, which perfectly illustrates the concept of fail-safe design. Engineers try to build machines that, when they inevitably break down, inherently default to a safe condition.
Like the dead man switch.
Exactly. It's a brilliant, albeit morbidly named example of this. You see it on lawnmowers, trains, and heavy machinery. It requires the operator to continuously apply pressure holding down a lever or a pedal to keep the machine running.
It accounts for the fragility of the human body. If the operator suffers a heart attack, faints, or simply trips and drops the tool, the switch loses that continuous pressure. The circuit breaks, and the machine halts instantly.
The failure of the human element actually triggers the safety mechanism rather than causing a runaway disaster.
So what does this all mean for you listening right now? You might never need to lock out an industrial boiler or measure the step potential of a downed power line. But the core philosophy of this material identifying hazards, understanding the hierarchy of controls, and designing fail-safes is incredibly applicable to everyday life.
Absolutely. The source material even mentions a concept called the 5S methodology. Sort, set in order, shine, standardize, sustain.
It's a Japanese organizational framework that revolutionized industrial efficiency, but it's really just rigorous housekeeping.
Exactly. And shine doesn't just mean wiping the dust off. In an industrial context, shine is actually a disguise for daily inspection.
How so?
When a worker is forced to clean a machine every single day, they're going to notice the microscopic oil leak or the hairline fracture in the metal long before it fails catastrophically.
Right. You can apply 5S to your own life, whether you are organizing a messy garage so you don't trip over a rake, which is eliminating a hazard rather than buying better shoes, or managing complex workflows. True safety and efficiency isn't about having great reflexes when things go wrong. It's about aggressively designing environments where accidents struggle to find a foothold.
It is about engineering a perfect system, but that actually brings up a lingering question we should leave you with today.
Okay, what is it?
We have spent this entire time talking about engineering out human error, building interlocking guards, dead man switches, and systems that automatically protect us from our own mistakes. But if we design our physical world so perfectly that human error is completely neutralized, do we risk creating an environment where people lose their natural situational awareness?
That's a great point.
If an operator knows the machine will always shut itself off if they make a mistake, do they stop paying attention? As we build taller and thicker guardrails around our lives, what happens to our human intuition on the day that the fail-safe itself inevitably fails?
That is a deeply compelling thought to chew on. We can build all the systems in the world, but outsourcing our own awareness might be the biggest hidden risk of all. Keep your eyes open, keep analyzing the hidden safety nets around you, and never stop questioning the systems you rely on every day. Thank you so much for diving into the material with us, and we will catch you on the next one.